what's a poor professor doing here, talking to a bunch of folks from industry, and especially because what I'm going to talk about, probably you folks have much better implementations to begin with. What we've been doing is building an open source NFV platform. And the primary reason for my coming and chatting with you folks today is to talk a little bit about some of the scheduling related problems that we've been trying to solve so that you can get really high performance NFV service chains. And I'm going to start by talking a little bit about our base platform. It's not to do a sales pitch on that, but so that you get to understand where we start from. And then afterwards, I'll talk a little bit at a high level about some of the problems that we've been solving in terms of scheduling. And it's work that I've been doing with a good collaborator of mine, Tim Wood from George Washington, and a bunch of our students. So this is something that you've heard all along, and we think that it's likely to continue to make inroads. And what we want to do is to see how we can go from just middle boxes that run as NFV in COTS hardware, instead be able to actually go to truly software-based networks and to be able to have platforms that can basically function as a bump in the wire. So this is stuff that you all know. We understand that it is important to address virtualization overheads. All these boundaries that you cross, the primary thing that we've worked on is to make sure that we avoid data copies. And the second thing that we work to make sure is that we do the right thing in terms of scheduling. So our base platform is, the goal has been to build something that is truly high speed in terms of packet delivery. We started actually with old, in fact, when we did this in 2013, we had machines from Intel that were probably 2-3 years older. And even with that, we feel like we've actually built systems that achieve pretty high performance. But the main thing is we get efficiency out of the system so that, I started actually at AT&T. I've worked for many, many years there, and that's where we started this whole activity. And what we wanted to do is to have an environment that provides a lot of flexibility, because we saw over the 20 years that I spent at AT&T that you go out, get a system, spend 5 years testing, and start deploying it. And by the time you finish deploying, it's become obsolete. And we see that having a software-based environment helps tremendously in terms of being able to deploy and keep up with technology. The main contribution for us is what you all already do, which is a shared memory framework that exploits DPDK and make sure that we do zero copy delivery to, in fact, wherever I say VMs, we've moved over to containers, and to be able to also have effective service chains where there is no data copy as well. And we've built a switching framework that allows us to dynamically adjust a flow's destination, not only in a flow dependent or a data dependent manner, but also state dependent based on the state of the data plane. And we recognize that you do want some notion of security, and what we've been doing is to make sure that we restrict access to packet data only among trusted containers or trusted network functions. We've put out an open source platform. These NFs run on containers, and we use the current version of DPDK, and basically have shared memory across NFs and shared memory between the base manager and the NFs. And lots of people have been using it. So if you look at the overall architecture, we have the notion of an NF manager that runs in the host user space. And these network functions run in containers. We are very careful about making sure that we are aware of NUMA-aware processing. We don't use interrupts at all. So we use the poll mode driver, and we ensure that there are no locks and allow for scaling. So if you look at the kind of throughput we get with a small number of cores, we can get well over 60 gig, and these NFs can start in less than half a second. So the idea is basically to make sure that even when you have service chains with lots of NFs running, you don't have to have copies for packet data. And so when you have applications that are running in containers, you can basically pass packet references to other NFs through a simple descriptor ring. And we also support multiple readers and a single writer, so you can have things like DPA, deep packet inspection, so on. And in terms of making sure that we have some level of trust, we ensure that trusted VMs are within a security boundary, and only those trusted NFs can access that packet data. So in terms of performance, we think we do pretty well, and especially when you go across service chains, the reduction in throughput is relatively small. Okay, so that's the base platform. What I want to talk about a little bit is what do we do in terms of scheduling and making sure that we can have service chains that function efficiently. So one piece that we've been looking at is to see that, if you look at a typical platform, you want to be able to host a large number of NFs for many different chains. And each flow ends up needing customized services. And not only that, you end up having many different flows, each one having a slightly different need. So if you look at having a monolithic NF, and you have multiple NFs that have to go through this, or multiple flows that have to go through these monolithic NFs that maybe start by what we built originally was to have a core dedicated per NF, and that certainly has scalability issues. We want to avoid that restriction. But also, we want to make sure that when you look at scheduling, you want to schedule packets so that you don't have interference between flows, and you have a very efficient way of classifying flows so that even when you have multiple flows that share a packet queue, you can get high performance without flow interference. So what we did was to say, what if we were to look at the flow as the scheduling entity, so that we can then say, if you've got a service chain of multiple NFs, then can you deploy a unique NF for each flow or for a class of flows? So what ends up happening then is that if you've got a service chain that each flow requires, can you start, let's say for a red flow, can you start up NF for that flow when it starts up? Think about TCP flows. And then you can go through a service chain that spans multiple cores. So we did this with a platform that we call Flurries. It's a set of algorithms and implementation where the main idea is to be able to have unique, short-lived network functions, and to be able to run these unique network functions on a per-flow basis at one extreme, or maybe for a class of flows. And the main idea there is that you can then do flow-level performance management. You can have flow-level isolation. Think about having a flow-level security appliance where you then say that I'm going to start up an NF for that flow process and then go away. So that way you end up getting customization for flows that get processed in the NF, and there's a lot of flexibility that you get out of it as well. So the scheduling work that we had to do, that was one of the most challenging issues to deal with here. How do you schedule these NFs? And how do you then move packets efficiently across these service chains? And another thing that you need to do is map these flows to NFs. So the primary scheduling framework that we had was to say that rather than purely depending on polling, what you want to do is to have a hybrid between polling for pulling packets off of the NIC to having some kind of interrupt-driven processing, okay, to be able to run thousands of NFs efficiently. And we have this notion of a flow director that maps flows to NFs, and a very lean library that basically recycles NFs. And the whole idea is to be able to have a system that can wake up NFs and recognize the priority that you have for NFs to be scheduled. And the benefit then is that if you look at the number of NFs that you can run on a core, if you do it straight with polling or with other approaches, you see a fairly significant drop in throughput. And what we can achieve here is basically full line rate if you think about 10 gigs, and be able to do that even if you have a large number of NFs that are running in a single core. And when you think about scale out, we can run up to 80,000 NFs in a second on a host, and also achieve reasonably high throughput even with that kind of multiplexing of NFs, 30 gig. And the amount of additional latency that you add is of the order of 20 to 30 microseconds. There's another piece that we've worked on, which I think is also important. I'll take just 2-3 more minutes, is to see how we can do scheduling for service chains where you don't see performance degradation because of bottlenecks within the service chain. And so the whole idea is to say that you want to be able to have a scheduling framework that recognizes what we typically worry about when you have a packet processing environment, which is that you want to have some kind of rate proportional scheduling. But when you look at hosts and operating systems, what you typically have is some kind of a cost proportional scheduler, which recognizes the amount of processing time that you take. So the idea here is you want to be able to, this seems to be running on its own. What we want to be able to do is to have a way of doing both rate and cost proportional scheduling. And so you want to have a scheduling framework that can have high throughput, but also fairness from the point of view of both having different packet flows that have different rates, as well as you have packets that might have vastly different processing time as you go through each NF. And so we have a way of tuning the base scheduler that you see with CFS. And also another important piece is to make sure that as you go through a complex service chain where you might have bottlenecks, you avoid wasted work, you don't drop packets unnecessarily, and isolate the bottlenecks. So we've worked on a back pressure system that avoids head-of-the-line blocking that you would have if you did this in a straightforward manner. So what we have is a way of basically adapting the Linux scheduler with C groups to be able to do this rate and cost proportional scheduling. And the other piece that we have is to make sure that we can be chain aware in terms of our scheduling framework. And we do that by using a reasonably interesting back pressure scheme that makes sure that we avoid wasted work within and across cores, and also make sure that we don't have head-of-the-line blocking. And any talk that I give will always have something to do with ECN, and we do exploit that capability to be able to make sure that if you have bottlenecks as you go through service chains that span multiple nodes, then you have a way of making sure that you can adapt on an end-to-end basis. So that's basically what I had to say. I can take 1 or 2 questions, or if he says my time is up, I'll stop.
We have time for a couple of questions.
Suppose one NF is one container. Is how many NF can run concurrently in the one server?
So when you look at the Flurries work that we did, we basically had a system where we had basically 24 cores, and we multiplex fast enough to be able to run 80K NFs in a second.
Yeah, I remember it's, that when I tried the 64 container per core, that system will always
done. So you have
done.
to have a way of scheduling these, having them go to sleep and wake up efficiently. It's not about having all of them running concurrently. At a time, yes, on a core you're running an NF, right?
Yeah.
But you want to multiplex them on that core.
Okay, yeah. So you must change the Linux scheduling, right? Do we need to change Linux scheduling?
So you need to adapt the Linux scheduler, yes. And that is where a lot of our work has been. Okay.
Okay. Thank you very much, KK.